But once again, my name is Chris Hall, and I'll be walking you through an introduction onto chaos theory. This is chaos theory applied to economics and the financial markets. And just to give you a little bit of background about information about myself, I do trade harmonics full time. I've been strictly trading harmonics over the last 8 years professionally. Throughout the years, I have involved chaos theory into every single step of my trading, and today I'm going to show you guys exactly how I do this. But let's first start off learning a little bit about chaos theory and how it can be useful to us. This is what we are going to be looking at. This is what we are going to be looking at today, and there's a lot of information here that we're going to cover, and some of the stuff as you look through it here on the PowerPoint will be standing out to you as things that you might have heard before in the past but not really understand what they mean. So these are the topics that we are going to be covering today, and yes, I know there are a lot, and we do have limited time to cover them, but you'll notice that we're not just going to tell you about, for instance, fractal dimensions, but how you can also take notice of fractal dimensions on the charts, what it means to you in your trading, and how you can use it. And we'll have this kind of outlook towards each of the subjects that we study in this lecture today. So let's see how history has defined chaos and order. Ancient Chinese thought that chaos and order are related, and this goes way back to the Chinese myth, where the dragon represents the principle of order, and yang then emerges from chaos. And that's important to note, because in some Chinese creation stories, a ray of pure light, or yin, emerges out of chaos and builds up the sky. So you can see how this was kind of used in history and in past cultures. Yin and yang were, or I guess still are, female and male, and that was the act to create the universe. But even after they emerge from chaos, yin and yang still retain the qualities of chaos, and that's really important to take notice of, because too much of either or brings back chaos. Okay, so they might be in perfect harmony right now, but either one being stronger will bring back chaos, and we can see that definitely in the market, which with the way price would react in time and how they're kind of reacting back and forth against each other. It also goes back to the ancient Greeks, and there was a cosmological poem that states that first of all chaos came to be, and then the earth and everything stable. So chaos, the Greeks have then accepted that chaos precedes order, right? In other words, that order comes from disorder. Okay, and I know this stuff might seem kind of dry, but it really does play a part into your deeper understanding. So when you look at the markets, you can tell when there's chaos, for instance, a news event, and when order can follow chaos. So chaos theory today is a new and exciting field of scientific inquiry, and it really is an astonishing and controversial discovery that most respectable scientists would have dismissed as a fantasy not that long ago. Like, if chaos theory fulfills its potential, it will dramatically change the way that we view the natural world and the universe around us, and also the way we definitely trade. And that's what, at least my results over the last 8 years, has definitely proven to me that chaos theory is something that if you can apply it, you can get that statistical edge that you need to carry on with your trading profitably. And you can see that on this chart. Why is it so fascinating? You can see that if you trade selective patterns, you can get a certain equity curve in your statement. If you decide to trade every single pattern, you'll get a different style equity curve in your statement, but from the beginning of the month to the end, you're still going to be gaining money consistently. And using chaos theory in order to enhance your trading is definitely something that can be used. So hands down, no question about it. If this is true or not, I guess if it's not true, I should be broke. And it shows that there are certain limitations to how someone can predict the future, because it is very complex, and no one can. And that's the thing that I want you to take away from this presentation, is that predictability is rare. You can always consider it as luck if someone was to say something and it actually happens. and that considering all that basically scientists filter out, which shows that it casts doubt on the whole traditional model building procedures of science. So how did chaos theory or chaos get here? Basically, breathtaking computing power now allows us to perform hundreds of calculations, backtesting, whatnot, as well as scientists get a whole different jar of monkeys that they can open up with computing power, and the rise of computing power that has accompanied by, obviously, the computing power that we have, is able to show us, and the random changes in weather and the changing populations of insects and birds, the rise and fall of civilizations, we can all go through simulations of these with computers and advanced computing power that we do have. These developments have definitely made an impact of almost every human endeavor that's ever happened, whether it be anything from mathematics, physics, astrology, biology, chemistry, medicine, economics. I really don't care. Everything right down to civilization and financial markets. Geometrical mathematics have definitely been a part of all of that. So I think we're at a point now where we should be able to create a meaning of what chaos theory is, and not just to the definition of everyone else that's out there, but to people like us who trade. Here's some examples you can read, but the example that sticks out in my mind that I think really applies to traders is variable dynamics of a nonlinear system. We know the market is nonlinear, and we have tons of variables within it. So that sounds like the perfect definition of what the market is and the chaos that we can apply to it. There are certain words that I guess come with any sort of new research and whatnot that goes into, in our case, chaos theory, and basically coined the language of love. Dynamic change, variable, and systems seem to be definitely high up there on the list. I think a lot of people confuse what these might be. Chaos is a dynamic occurrence. Okay, it occurs when something changes. So what is changeable in a given situation is referred to as a variable, and you know that from your high school, like algebra and whatnot. Secondly, any entity that changes with time is called a system, and systems have variables, as you know, such as the populations of penguins in the Antarctic, the flu moving through a country, a school where people may move through grades. Change is inevitable. And there's a phrase, and it says, change is inevitable except from a vending machine, right? And that's definitely what helps us describe a system. So we can define a system in two different ways, okay? We know that basically you have linear systems and nonlinear systems. An example of an all-knowing system would be an old-fashioned grandfather clock. You could also take the balls on a snooker pool table, behave within the boundaries of a deterministic system. Linear systems variables are simple, relatively, and directly related. Linear you can predict, right? Like a simple equation where the variables involved only appear to the power of 1. So the result of an equation of something like 5x plus 2y equals 10 can be solved and would look like a straight line drawn on a graph, and I'll show you an example in a second. In a nonlinear system, relationships involve powers other than 1, right? For example, a nonlinear equation might be something like 3b to the power 2 plus 4c to the power 3, which would be graphed as kind of like a squiggly line. And you would probably really need the help of some sort of a computer to understand that. And then we have sort of like language of love words to do with defining a system. And a period is an interval of time by an occurrence of a certain condition or an event, right? And a variable in a periodic system explains that it exactly repeats its past behavior after the message of a fixed interval of time, kind of like a swinging pendulum. When no variable affecting the state of the system undergoes a completely regular repetition of values. Remember, guys, aperiodic behavior, visualize something like the flow of water going down the sink. It's kind of like chaos. You don't really have any sort of variables that you can predict what's going to happen. It's very irregular. So here's the graph I promised you on linear. Linear systems, of course, chaotic in the occurrence of aperiodic apparent random events in some sort of deterministic system. Remember, yin and yang, after chaos there is order, and in order there is chaos. So linear systems are predictable. For example, a straight line drawn on a graph, you know where the line is going to be going next. Then you have nonlinear. Nonlinear systems, these systems cannot be solved. Most of the world around us operates in nonlinear equations. We just do not have to put them in practical use because scientists would dumb them down into linear equations to make more sense of them. An example of that is, the force of a car moving on the ground can be measured by mass times acceleration. But a nonlinear equation would take into account of friction. This changes the whole rule systems and makes it difficult to predict what will happen. Remember, you cannot predict a nonlinear system that is aperiodic. So who's this guy? Let's continue with our math geeks. This is going to be Benoit Mandelbrot, and you can read some information there about him. But his first book was the fractals. It was called Forms, Chance, and Dimensions. His second book, of course, the more popular one, The Fractal Geometry of Nature, is actually what caught the attention of a lot of scientists and made them really think about chaos theory and how it would all work. So this guy started his work, obviously, in economics and found that each price change was random and unpredictable, but the sequence of changes itself was independent of scale. Okay, so in other words, the degree of vibration remained consistent no matter what happened in the world. A war, an earthquake, it didn't matter because it was all within chaos, and within chaos there's order. And we're going to look into that. You can kind of hold on to that line because we're going to look at a chart soon. I'll show you exactly what that means. So he used to work on telephone lines to transmit information from computer to computer. He divided the time into twos until there was no noise, and this is what a lot of you would remember as a Cantor set, because there was always some bits that would have no noise at all. After breaking them down into twos and breaking those into twos and those into twos and on and on and on, one time free period with no errors are then found, and you can use that to transmit data. So if you know anything about computers, you'll know that the noise inside of a telephone line is very bothersome. So you can imagine sending thing like data across from one computer to another can get corrupted between the two if you were to have something like that to happen and have a lot of noise. So engineers didn't know what to do, so Mandelbrot came up with the Cantor set, and this was able to solve their issues as well. But as he was the father of fractals, this little well-known paper called How Long is the Coast of Great Britain, which most of you have probably heard about, he asked a question about this, basically measuring the size of Great Britain. And basically, there was something that, I don't know, if you use a 10-cent measuring stick that will fit into more nooks and crannies than if there was a 3-meter long measuring stick. And one that's 1 centimeter long will fit into even more. So how do you measure the coast of Great Britain? And each will change the length of the coast, obviously, depending on how long you use for a measuring stick. So that was his whole beginnings into fractals. You can see some of the images there of fractals with the Mandelbrot set on the right and the piece of nature that you can see fractals in, how plants grow in fractals. And of course, that then brings on the question, what is fractal dimension? Okay, in this well-known paper that he did write, he talks about fractal dimension and how the shape of a 2D object will be apparent as 2D because you're so far away. Like, for example, a star. When you're far away from something, the dimension of what you're looking at is different than when you're standing right next to it. So because of this, the closer you get, the more details added. And say you were standing, I don't know, a couple hundred feet away from this orange sort of 2D circle, you might not know that it's actually a basketball. So fractal dimensions, what is that? That's actually the points between the 2D and the 3D. Okay, so in between those points, that's the fractal dimension. The geometry that we're all used to goes back to the Greek maths, okay? Shapes like regular triangles and squares and things that we're used to. Fractals are different, okay? They are irregular shapes. Fractals are a way of measuring quantities that otherwise have no clear definition. The degree of roughness or brokenness or irregularity in an object, okay? So in other words, fractals are a way of seeing to infinity. Self-similar implies that any subsystem of a fractal system is equivalent to the whole system. Okay, so the little bit that you're seeing is obviously going to be a part of a much bigger picture. And the fractal triangle, for instance, very popular image, you can see that the triangle is structured identical to the large one before it. Okay, so some fractals are only statistically self-similar. Their magnified smaller pieces do not superimpose on the entire system, but they do have some general type of appearance. Within the overall shape, there is a relative pattern whose substructure basically characterizes the nature of chaos, indicating when forecasting breaks down. And that's important to notice. But we'll talk about that more because fractals are everywhere in the market. Okay, also in nature. When you have fractals in life and the universe, we can see them in the market. Probability can be increased while trading. Fractals can make very beautiful computer graphics based off math. And and that's what basically fractals are. Fractals are essentially, if you look at this image here, something that could be going on for affinity and affinity. Okay, so let's keep on going. Why use fractals? Most people don't realize when watching Avatar, the film was generated on computers using fractals. They play a huge part in special effects, but they can play a very important part on your bottom line. Seeing one pattern form on a daily and then seeing another of the same on the 4-hour and the same on a 1-hour is a very nice path to be on. Those are what you want to see when you see fractals and fractal dimension. And here you can see an example. The chart on the left's a 15-minute. The chart was a 4-hour chart taken slightly after, and you can see the two together. There was a very powerful move. Now, it's not always going to be like that, but it was a good example to show you how you can have self-similar harmonics within the actual market. So let's continue on. This is Edward Lorenz, originally a meteorologist, first to record the known existence of chaotic behavior, and went to MIT to head the Department of Statistical Weather Forecasting, being the first to obviously record this chaotic behavior. He obviously was also, he built the first mathematical generated chaos that he had countered by using some sort of primitive model of a global weather system. This model gave him a rough idea of how weather behaved and contained in 12 or so variables. Later on, using computers that would mock the Earth's atmosphere and oceans, he studied interrelational sort of between the whole nonlinear meteorological factors such as temperature, pressure, and wind. And he found some interesting stuff. That very small changes in the initial condition of the environment produced widely varying and unpredictable responses. How could a simple sort of 3-equation model give such a bizarre result, was his question. His work was then published in a paper, and I put it up there for you guys to download. I'll leave it you to read it. It's not the easiest read, but it will deepen your understanding further for those of you who did want to know more. But essentially, one day Lorenz was playing with this weather machine, and he was inputting some data, and he decided to shortcut and put a number as 0.506 instead of 0.506127. Of course, after coming back from getting a coffee, he was shocked to see what he saw. He realized by leaving out some of the differences of 127 and putting in just a 506 that those initial conditions changed everything. Here's what Lorenz said, and I quote, "It implies that two states differing by imperceptible amounts may eventually evolve into two considerably different states. If, then, there is any error whatsoever in obstructing the present state, and in any real system, such error is inevitable. An acceptable prediction of the state of any distant future would basically be impossible to be known. So you cannot predict the future because these small little sort of differences that can occur initially." And the whole example of this in his studies goes into a water wheel. And at certain slow speeds, the system works fine. But when the water fills faster, buckets don't have enough time to fill or empty the system, and it then becomes chaotic. The system will then slow down or reverse, but the movement is never going to be predictable. And when you plot this chaos, it will look something like this. Okay, this is an attractor and how that water wheel movement would be graphed. So finally, this is what you guys have been waiting for. Let's put this all together. This is an attractor, this yellow line. And this attractor is, this is a chart, I believe, of the euro yen. And we are looking at, I'm just going to get a pen out here. These are our support and resistance zones. These are obviously the resistance zones. And this is our attractor, this yellow line. You can see how many times price has been attracted to it. It's kind of like a magnet, right? So this is what you're looking for. And you can visually see this. This is not something where you need a computer to do it. You can visually see where this attractor line is. Price will always come back, go around it. You don't want to be taking trades when you're at the line of the attractor. Depending on what side you're on it, you'd rather be long or short, but you want to be taking your trades at the extremes. Now this is what I was saying. I'm a harmonic trader, so I look for these sort of patterns to come into play for me to take a trade. Once this pure Z zone, if you haven't seen the videos on it yet, go check them out, fxgroundworks.com. You can see some on YouTube /fxgroundworks. Once this pure Z zone is formed in the area of support and resistance extremes away from this Lorenz attractor, then we can get a very high probability trade. Okay, so here's a live chart of this trade that we've taken. Our entry was 125.13, and we're now just above 126.33, up over 100 pips. We are looking at a move back to this attractor line of 131.25, which will give us about 600 pips in order to hit this area in here. So this is what we do. This is what we do day in, day out. We look for these support and resistance zones. We look for harmonic patterns, and that's the key. You need a harmonic pattern to do this. Up in here, the pattern could be up in here, it could be up in here, because this is a big area, so that's why you need harmonics to do that, and that's all we do, day in and day out, and that's what gives us the results that we have. Last month we did about 1,238 pips. Month before that it was 936. So we do quite well, and And this is a proof here, chaos does help you with your trading. Once you understand it, you'll be able to definitely look at those attractor lines, and that's what we teach at fxgroundworks.com. So if you are interested in learning harmonics and how to apply chaos theory to them, this is the harmonic here. You can see the little pattern down here. This is why we got in, and this is why we are successful at what we're doing. So if you have any questions, by all means, shoot me an email. My email address is Chris, H-C-H-R-I-S-H, at fxgroundworks.com. Let me see if I can just write that up there for you guys, in case you did not get it. There you go. That's my email. If you have any questions, just shoot me an email, let me know. By all means, hopefully I'll see you inside the members area. We do these webinars quite often in there and have a whole bunch of different lessons on how to apply different sort of chaos theory as well as other subjects, logic, and all that stuff to the markets. So if you do care to join us, you're welcome to. And otherwise, hope you enjoyed and found this lecture on chaos theory and the markets very informative.